for presentation can be loading it up on his computer, or on the computer with us. Okay, so are we live? Perfect. Any?
Yeah.
And the grades are uploaded in the website, so you guys can take a look. The same place that in the schedule.
Okay, team 10.
Yes, at 3 minutes, there will be like a noisy sound, so you should stop at 3 minutes. So we got actually like lots of things here, so we're going to be a little bit strict.
I'm like beginning.
Yeah, we're on it.
Yeah. There is a pointer here if you want.
We got one. Oh, we got it.
We got a pointer?
Yeah.
Good.
Okay.
Yeah, please.
Okay. There you go. I think they're good.
Okay, so let me know when you guys are ready. Okay,
Yeah, we're ready.
okay, go ahead.
All right, guys. So we're Team 10, and the case study that we wanted to look at was using GPR to try and combat contagious citrus greening disease. So a bit of setup for the problem. Basically, in 2005, this contagious citrus disease traveled to Florida and was infecting their orange trees, and it still is. And basically, it causes all the oranges to be green and bitter, and they're not sellable. So this case study was wondering, can you use 3D GPR to provide a non-invasive method for mapping the root systems of these orange trees?
Okay, since we are dealing with GPR, our physical properties are going to be electrical conductivity and dielectric permittivity. GPR data was collected at 2 sites where the majority of soil consisted of sand, which has a low conductivity. Therefore, our diagnostic property is going to be dielectric permittivity, specifically looking at the contrast between the soil and roots. Next slide, please. Survey, they used a shielded GPR device for a zero offset survey with antenna central frequency of 2,600 megahertz. This was mounted onto a push cart and wheeled around a grid of 120 centimeters by 80 centimeter, and it's done just by the tree, in front of the tree.
So the data found that the greatest depth of survey is 40 to 50 centimeters. Based on the image above, the white dots are the primary tree roots, so the greater tree roots, whereas the smaller dots are the secondary and tertiary tree roots.
So we would want to use a pipe fitting app in theory similar to the one found in class. There were some issues with that one due to size constraints, so we couldn't actually fully use that one. We would use it to see the diameter of the tree roots and see how the disease restructured their system. This is not what they did in the report itself, but we'll also describe what they did in the report.
So once they were able to collect all the data, they compiled it and processed it into a 3D point cloud cube, which then rendered this nice, beautiful map of all the roots. And what's really interesting is that they were actually able to distinguish the roots from the tree of interest and the other roots from other trees.
So here you can see 2 plots of the tree roots within, showing their extent to length and depth. That was kind of their goal, was to essentially figure out the tree root structure.
So the case study found that GPR can be used to map the tree root structure. To find roots at greater depth, they want to use lower frequency. As well, we are thinking of using a pipe fitting app to map the to map the diameters of the tree roots. Is that it?
That's it.
Perfect.
Whoa, perfect.
Perfect timing. Do you guys have any questions for us?
So did they talk about the connectivity of the soil, and was that taken into account?
Not really in the paper, but they just said mostly of it was sand, and there's a bit of clay and silt in here. But in two sites, there's one that's poorly drained and one that's moderately drained. But mostly it's just going to be sand.
I think the two sites they were looking at were relatively similar, so finding differences in connectivity of the soil wouldn't really matter that much.
Any more questions?
Were they able to look at the roots from healthy trees versus diseased trees?
Yeah, they didn't really. I think they all looked at infected trees, which was kind of counterintuitive to what I would have thought they would have done. Because I mean, our kind of question was, well, can we look at diseased trees and non-diseased trees and see how the disease is or how it's affecting their root structure? But I think they just looked at 4 to 6 trees that were infected at varying stages of the disease. So some trees were like near death almost, and some trees had just contracted the disease.
One last question while you're checking. What sort of things in the app would you like to have seen? You said it was limited.
Yeah, so we kind of got together, I don't know if the slides are in there, we tried to do it with these two, but we couldn't. And so it would be similar idea to the pipe fitting app itself. So it's in, it's online right now, where you would find the diameter you would solve for the radius of the pipe, but instead we would solve for the radius of the root instead.
Yeah, Wei-Han was
It
doing
was the
some
scaling that's wrong. So in the pipe fitting one, the y-axis was time, but in the radiogram that they had, the y-axis was depth. So we had to convert it somehow, and we thought if we used one of the app, what's that? The attenuation app, we just plug in some kind of dielectric permittivity for sandy soils with a conductivity of around 0.1 to 0.01. We can find the velocity. Then with the velocity, we convert that to centimeters per nanosecond. So now our time in the pipe fitting app is in nanoseconds. So if we just take the centimeters per nanoseconds, we can get centimeters for the y-axis, and it'll be similar to the radiogram. Yeah, so now we divide the scale everything by 50, and instead of 0 to 40 meters, which is shown in the pipe fitting app, now it's around 0 to 80 centimeters, which is around the same x-axis as the radiogram from the case study. And then with the velocity, we converted the y-axis to 0 to 65 centimeters. And since their maximum depth is 40 to 50, I think it'll roughly cover whatever hyperbolas that we see in the case study. But the problem with that is in the pipe fitting app, they have h, so that's depth to the center of the pipe and then the radius. And when we when we scale it, we divide everything by 50. And what happens is the maximum depth to the pipe on the pipe fitting app will become something like 4 centimeters. And that's way too shallow. You see, their minimum one is like, with the black dot, I think it's around 8 centimeters. So it's already over our scale. It's too much.
That's it. Sweet. Thank you.
I'm good.
Samantha, where do I get those evaluations?
Oh, here.
Guess I'm gonna drive the projector. So I'll just look through this.
Okay, so you guys are ready?
Yeah, sure. All right, so we're team 4, and we also decided to use ground penetrating radar, but we're looking at using it to characterize chum salmon habitat, spawning habitat in a river in northern Yukon. So just some background for this problem. This is a river where chum salmon do spawn. However, there's been a lot less salmon that have come back to spawn in recent years. Something that's important is that it's an important subsistence fishery for a local First Nation. And something that's interesting is that it's well documented that chum salmon spawn in areas where groundwater upwells. What's also interesting about this part of the world is that there's a lot of karst in the underlying superficial geology of this riverbed. And we think that there's a possibility to explore using ground penetrating radar to try and better understand where the karst topography is. And that's important because understanding where that karst topography is can help better manage the fishery in this region.
We're going to quickly talk about the properties. So the property that we're interested in is dielectric permittivity. The background values we're expecting is for sand and gravel, so between 3 and 5, and limestone between 4 and 8. And we're looking at karst, so it's going to depend whether they're filled with air or with water. So with air, we're going to be around 1, with groundwater, we're going to be around 80.
And since we're dealing with dielectric permittivity, the best survey to use would be GPR, of course. And that's ideal since what we're looking for are voids in the karst, and that's usually between 0 to 10 meters in depth. So that's perfect for us. And what we wanted to use as a survey would be the common offset survey, and that would help us identify interspaces between voids, limestones, and alluvium.
In order to conduct a survey, some transects that are perpendicular to the river channel are going to be made. That is because it is easier to get information for the areas between. Also, the transects also provide a wider survey area so that the data is more comprehensive. And it is better to take the survey at low flows when the river is still waveful.
As for processing, we were going to resolve the travel time to depth because the waves are going down and bouncing off and then coming back, so you have to account for the fact that it's traveling the distance twice. And then once we got the data, we would work on smoothing and stacking it to get rid of the noise and let us be able to better see what we were actually looking for, which is our voids filled with water. Moving on to interpreting. Since this survey actually hasn't been conducted, we use the app to show you an example of what would happen if we were to encounter voids in the alluvium. So our dielectric permittivity for the alluvium was 4, and for the voids it was 80 if they were filled with water, and you can see that they're reflecting off quite noticeably in comparison.
I think we'll leave it at that, but we think that the survey would work best if the voids are actually filled with water.
Questions? Yes.
So how would finding karst help you solve the problem about this?
That's a good question. So this is actually something that fisheries consultants are working on right now, and it's kind of just the first step in their problem is trying to determine where there is actually fish spawning, just so they can better understand how to manage that resource. So it's not a smoking gun from a management perspective, but I think it's a way to better inform the management of the system. They're using different methods to try and determine where it is right now, telemetry and that kind of thing.
So in those references that you have they been used to try to find these karst tunnels?
So I'm not sure if they're actually trying to locate the karst underground, but I know that they're trying to determine areas of upwelling by doing a temperature survey in the surface water. And they're also, like I said, they're using telemetry, so they tag the fish, and then they'll based on, they read where the fish are at different times of year and will infer where they're spawning that way. So this is just another possible way to try and identify, where they might be spawning if it is in fact controlled by karst. So
the salmon don't necessarily come up the river; they actually go down through karst tunnels.
No. But if there's groundwater flow, shallow groundwater flow underneath the channel, conceivably there might be pathways through karst tunnels, and where that would infill or flow into the river. So areas of upwelling, that's where fish spawn is where there is upwelling into the riverbed.
Good.
Okay, guys, you ready?
Yeah.
Okay, go ahead.
Okay, so for our project, we took a look at using geophysical methods for identifying buried avalanche victims. So in terms of the setup, avalanches kill about 14 people every year in Canada from burial, and it's like a time-sensitive thing, so the rates of survival pretty steeply decrease the longer they're buried. So looking at geophysical methods that can help quickly identify buried people. So the properties in our scenario, snow is a pretty poor conductor when it's dry. And the human body is like mostly liquid, relatively conductive, so there's a good contrast there. Metal objects that are associated with people like skiing and snowboarding and stuff in the backcountry, skis, snowboards also provide good contrast. And again, another property, dielectric permittivity, you get a good contrast against the human body and snow in the background. So yeah, to our survey, GPR is sensitive to those. It's sensitive to conductivity and dielectric permittivity. So if you look at the chart to the left there, it kind of shows a summary of the different properties of avalanche-associated material. So there's good contrast between like the body and the background of the snow, but there can be a little bit of interference from like associated debris like trees and rocks and the things that you'd expect to be buried. So when you're surveying for an avalanche, often like the surface can be rough, so you need to have it pretty portable. And again, like with the time sensitivity, you need to be able to quickly survey a fairly large area and also be able to rapidly process and read out the data. So GPR, again, this image here just kind of shows you get a good contrast from the various objects, like a metal plate shows a good contrast against the background, and like the BME is a body mass equivalent, so you see there's a good contrast against the background, but being able to distinguish between, okay, what's a body, what's a tree, and what's a log becomes a little bit more difficult. So one of the ways the paper I was looking at did that is that you can look at the individual wavelets received, and you can notice that there's a pretty good distinction between what a rock or a tree wavelet looks like versus what a body mass looks like. And in terms of synthesis, a quick way to add more data after you identify a potential target with GPR is just probing, and you can tell the difference between whether you're in contact with a rock or a log versus a human body. And another interesting factor that the GPR is still sensitive to is that over time, as the body is buried, there's like a development of an air cavity around the body as the snow melts and ice and freezing in the skin. And the paper just found that GPR is still able to detect bodies like as the body freezes as time goes on. So in terms of modeling it with the applet, you can model different positions and different properties of the background, and you're able to vary the object properties and kind of see it. But it'd be interesting to be able to put a few more things in there to kind of be able to understand the influence of background associated debris and being able to differentiate them between things of different properties in the applet.
So on your slide, there's a comments about selecting the frequency, and it was like a 400 megahertz.
So those are just the two available surveys that they presented in the paper, and it was just talking about how those two resolutions were sufficient for picking up on bodies and other equivalent things.
Have you kind of thought about why that's like enough, to see the bodies?
Well, yeah, like we modeled that as well using the app, and you can kind of tell like the depth here is like much. I put these at like 2 meters, and you can tell that the depth of being able to see at that frequency is like much greater than you would ever really see in a real world avalanche. Like be equivalent to like a 12-meter depth, which would be bigger than you typically see in an avalanche. So it just shows that like the skin depth and the resolution is good enough at those common frequencies.
These layers that you were talking about when a body is freezing, how quickly do those form? I mean, the person's only going to live there for what, half an hour?
Well,
how long
if you look at the,
how long can people survive?
This chart
like that?
Here kind of shows just like the distribution of survivability percentage after like you're buried for like 15 minutes, survival is about 90%, but as you get on to like 35 minutes, survival kind of plateaus here, and you got about a 30% chance of survival for that like 30-minute to like hour and a half, 2 hour range. So you're kind of looking in that kind of time range.
And that different ice layer that you were talking about, how long does it take for that to form?
So this actual wavelet is what they surveyed at 1.7 hours, and it's equivalent to like some of their higher model things. So they do form pretty quickly, just like as the body's in contact with snow, it melts pretty quick.
I don't know.
Hey, you guys have a fit?
Yeah, we're good.
Go ahead.
Hey guys, we're Team 9. We're talking about the hazards associated with landslide dams. So if there's ever a landslide that blocks a body of water or a stream or anything like that, you can end up with damming of water behind it. And if that fails, which they often do quite unpredictably, you can end up with fairly significant hazards. So part of the issue is that they can be really complex and vary a lot depending on the material that created the slide in the first place. And so understanding these is quite complex. The other thing is that they typically fail quite early on in their lifetime. So it's important to characterize them quickly, which we're thinking that geophysics can be very helpful with. So again, just reiterating the problem, in the event that a landslide dam does fail, which they typically do within sort of a year or so, you can end up with fairly large disasters on your hands. So ideally, our app is fairly large and probably would be fairly complex to make, but essentially, ideally we'll do two things. The first is to model the landslide. So you would say the type of flow you want to model, whether it's like a rock topple or a debris avalanche or a debris flow, anything like that, as well as how far it goes, the size of the channel that it's blocking, etc. And then you would actually be able to customize your survey. So select the relevant properties that you would then want to discuss. So Josh is going to talk about the 7-step framework.
7-step framework got 7 steps, starting with the setup. So the big question here is obviously, can a geophysical survey identify key physical properties of the various materials in this landslide dam? So to do that, starting off, physical properties, what we got? Well, we're looking at the densities, the elastic moduli, that's kind of interesting to us. So we're going to look at sort of a seismic survey for that probably. And then we thought GPR would probably be handy too for looking at electrical conductivity or dielectric permittivity, handy little physical properties that we could have under our belt. The surveys to do that, as I said, GPR and seismic, that's the way to go, that's what we're doing. Yeah, just obviously they're useful for different things. So the GPR is going to be helpful for us finding the thickness, while the seismic might be good for, figuring out the densities and such. The actual data that you'd collect, again, the different surveys would give you different data, as I kind of just said. But the water table's quite an interesting thing because you'd probably be getting that from some sort of midpoint gather. So yeah, next one. And yeah.
So moving on to processing, as Andrew mentioned, you're going to start out by inputting parameters into the app based on the type of slide, the source material, how far it moves, and of course, what actual survey you're doing. And then you'll take the data that you collected during the data phase and you'll put that into the other part of the app. And that'll give you, not yet, That'll give you some lovely things. And you can do all sorts of stuff to that with the app. That is labeled in the slide. Interpretation, you can then look at both the model and the things created in the app and compare them to find things like anomalies, location, depth, and so on. And using all these things based on a series of different surveys, you can figure out exactly what is going on inside your landslide dam.
Was there actually a landslide with Bigham Canyon?
Yes, there was a landslide, but it did not dam anything. We just thought it was a pretty picture and representative of just the size and scale of certain landslides.
So is that actually common that you have landslides that are really affecting tailing dams or various kinds of dams?
Usually, so it's typically the landslide that occurs will just obstruct a generic flow channel, and that will create a dam behind the slide. So it won't actually be affecting a dam that exists in real life. It will create a dam. But again, most dams that are man-made have been carefully designed in order to not fail, in order to be effective, whereas a landslide, it's typically very poorly consolidated material and not designed at all, so it typically fails quite quickly.
We could be worried about things like whether it could change the course of the river, whether it might fail again and damage anything further downstream, and so on.
Good. Good question.
Have you thought of, if there was a question, go ahead.
Oh, yeah. Would you consider doing numerous surveys to try and track of whether or not?
Yeah, definitely. So that was part of the hope with this theoretical app that we were mentioning is you could actually, for one set of landslide parameters, you could do multiple geophysical surveys in the app to figure out kind of what will model it most effectively. And then again, you could, in theory, add another component of the app to track how it could deform over time. But again, you need a lot more parameters. So I'm sure someone could design it. But.
Go ahead.
Okay, so our case study was it was conducted following an earthquake in central Italy in 2009. There was a devastating earthquake in Abruzzo, Italy. And so following this earthquake, there was a government study that was multidisciplinary, and they were hoping to figure out if they could somehow predict these earthquakes in the future.
So the main properties they were doing with their survey was they were measuring the electromagnetic induction around this area. And so the two main physical properties associated with that were electrical resistivity and magnetic susceptibility.
So to set up a survey was a really long-term survey. So they created 3 different stations where they buried their monitoring device about 2 meters below the surface. And this area you see is about a radius of 10 kilometers. So they're trying to measure data in basically the entire fault zone to see if they can predict future earthquakes in the area and try to mitigate damage. And from the data they gathered from that over the 4 years, they formatted into sort of just a table. So when the piece of data and the measurement was taken, And they were looking at the magnetic fields in each direction, like as you can see, Vx, Vy, and Vz. They then used MATLAB to process all of their data.
So then when they took the data, they used the phase of induced magnetic field calculated from the MATLAB, and they hope that in the future they'll be able to use this in monitoring the earthquake activity of the area. And right now, they haven't really come to a conclusion that it's indicative of seismic events in the future, but they hope to see stable measurements and not have another earthquake.
A lot of their lack of conclusions also happens to do with the fact they haven't had another major earthquake, so they've had nothing to predict.
In terms of an app that would be needed to do this, we need one to compile and process large amounts of data in terms of years. And we would need it to calculate induced magnetic fields as well as the magnitude and phase of induction.
So, I'm a little bit confused about what they were really trying to do here. Sorry, they're trying to look at magnetic fields as a precursor to the earthquake. That's the idea.
So they're
correlate the two.
Yeah, their hypothesis is that magnetic fields drastically change right before a seismic event. They're hoping to create a monitoring system in order to prevent a lot of damage and loss of human life.
So when you talk about induction here, are you talking about sort of the same kind of thing that we were talking about, like with, like an EM31, or where you've got an active source, and then you're looking at you've got to determine the phase of the induction?
There was an active source at a set frequency. I can't remember what frequency they were using offhand, but it was an active source with 3 different monitoring stations, each one acting as a receiver and source. So each one was compiling data individually.
Do you know what that source was?
It was a lot. I know it was similar in setup to kind of an EM31, just much bigger in scale.
So that they actually ran perhaps a wire around this, or did they have a big current or something going in?
They had a big current going in. It was all solar powered. So at each of the individual 3 stations, they had solar panels setting up to put a current in at a set frequency.
Okay, I'm not sure I understand.
So go ahead. We are team 8, and we decided to do a project on geotechnical engineering of pipelines, and we chose to use SEISMIC. So basically, when installing a pipeline, it is best to avoid bedrock in terms of project cost and timeline. So our main question we're trying to answer is, where is the shallow bedrock located along the pipeline pathway?
So the physical property that we're going to use is seismic velocity, and also looking at the relationship between seismic velocity and density. In general, the denser the material, the faster the higher the seismic velocity is. The type of survey we'll do is a seismic refraction tomography. It basically uses a big weight or like a large explosive source. And it's set up sort of, as you can see in the picture, with like a big sort of linear array with a bunch of different geophones all set up like that. And this is an example of the data we can get with the arrival times in the vertical axis, and along the bottom it's the trace number, or like the horizontal distance.
Okay, so while analyzing our results, we have to consider a few things like low velocity zones, hidden layers, dipping layers, and irregular layers. As far as interpreting results, high velocities you can see correspond with bedrock or dense soils, where intermediate velocities are a little bit more complicated. Yeah. For synthesis, so this involves just like reviewing our results and calibrating interpretation with known published values and deciding if our results are appropriate and if further testing will be needed.
To use the seismic refraction applet, we wanted to answer this specific question. Can the seismic refraction applet itself be used to delineate the depth to bedrock with sufficient accuracy of just around less than 2 meters? Because in terms of pipeline applications, the difference between 5 meters of soil cover and 40 meters of soil cover in terms of construction isn't very high. So you need sufficient accuracy in the shallow depths. So to do this, we assumed a 3-layer model, all horizontal, with the 3 velocities shown here. Dry soil with 500 meters per second, wet soil 1500, and bedrock or dense soil at 4500. And we want to figure out how difficult it is to locate the depth to bedrock with little soil cover. So trial 1, the image you see is using the default parameters in the applet, whereas trial 2 and 3 alter the depth to bedrock from 5 meters to 2 meters. And as I said before, that difference is quite important in pipeline considerations. So we want to see how the applet kind of shows that. And you can barely see a difference with this applet. So to answer your original question, probably not. You can't sufficiently use it to see how deep bedrock is.
Have you thought about like, okay, what could you do to get a better resolution to figure out that part?
Maybe alter the source or the receiver geometry, frequency. I have no idea. Yeah.
So once you discovered that this app would help you, did you consider any others that you use?
No, because we put the app in pretty last minute. We assumed the case history was good enough, and to somehow figure out a way to use the app was quite challenging. So we would ideally want an app with better resolution.
Can you just go back to the comparison, like with
this one? To the naked eye, it's pretty challenging. There is a difference if you look hard enough.
Okay, so what are you going to try to do to see if you could get better resolution?
No, we didn't get into that. No, we just need to see if we do it or not.
Yeah.
Which team? 7. I uploaded like 6 times in less than 10 minutes. Yeah, like I uploaded. Yeah, I just like uploaded like 6 different versions. Okay, hey everyone. We're Team 7. So we decided to talk about geophysics and enhanced oil recovery. So what is enhanced oil recovery real quick? It's just a tertiary stage of production within an oil well. So primary and secondary production already occurs when they find the well and they decide to pump about anywhere from 5 to 50% of the oil out of it already. So EOR would help recover an additional 10 to 30% of the oil already from that developed reservoir. So it's really economically beneficial to companies because they already have these discovered wells and they're going to be able to use different methods to be able to get more out of it. So
a lot of times these oils sit on sedimentary layers, like sandstones, carbonates, shales. So we should be able to answer questions such as where are the boundaries of these reservoirs, like where are they located, and where can we put optimal locations for injector wells to help EOR do its job. So the physical property we wanted to look at specifically was seismic velocity. So in these sedimentary layers, such as sandstone carbonates, it's especially vulnerable to seismic surveying because sandstone has a velocity of upwards of 2,000 meters per second, where oil is going to be more in the 1,200 range. So it's going to have a significant difference. We did take a look at GPR and DC resistivity as well, but they would likely be already considered in the primary and secondary production of these wells. So we won't be looking at those quite as in depth. So when it comes to surveying, we're going to take a look at a CMP survey, or common midpoint gather survey, which is pretty standard for this kind of surveying. So subsurface points in this case would be sampled more than once. So that would give you a more accurate representation of what you could see underground. And the shot would be generated by different means based on the surface conditions in your land and water. We've taken a look at this versus explosive hammer shots, vibrosis, that kind of stuff.
Yeah, so like the seismic data gets recorded in the form of multiple wavelets from the geothermal sources. And you create a best fit line, and from those lines you calculate the return times. And we decided that one of the class apps that could be used to help visualize this is the SEISMIC applet. And it would vary, of course, with the situation, but you can kind of fiddle around and create different scenarios based on the expected seismic velocities for oil-bearing layers versus sandstones, because we expect the oil-bearing layer to be bounded by a sandstone. So again, based on the site specifics, you can kind of get an idea of what the return times are going to be for the reflected waves map.
And then using that, we could take a look at the seismic reflection app and also construct a seismic trace in which that you would fit a line. You can find the intercept time to see how long it would take for that reflection to hit that oil layer and the boundary and to come back to see hopefully kind of the extent of where the reservoir extends to. In terms of processing, we know that there's a lot of noisy data that can occur. So, but fortunately for our common midpoint gather survey, we have a lot of multiple survey points, so that we should be able to stack and filter that kind of stuff to correct for those noise.
And again, yeah, for the common midpoint, the main form of processing you're going to do is the NMO correction, and there is an app for that. So following the procedure outlined there, you can kind of use a curve fitting method to see how that's going to be corrected.
And in terms of interpretation, our combination of these stacked filtered seismograms can help us make a profile, VSP, which provides important information about the time depth function. So it can also help us identify direct hydrocarbon indicators that are identified through changes in pore fluid, fraction intensity, lithology within the unit, that kind of stuff. And then finally, our synthesis, we just wanted to end with saying that from these seismograms, we can hopefully use 3D ray tracing techniques and wave equation methods to make a seismic profile, such as this one. And it's important because it's economically beneficial to the companies involved, and they help distinguish these oil boundaries from water. And the only limitation to these apps we really wanted to address is that they're currently limited to 3 layers, while in actuality geology could be much more complex than that. You could have oil stacked in between multiple layers. So, yeah.
So here, the topic was EOR, right? Yeah. So were you thinking about that as monitoring, or the material was about more like finding a reservoir?
Yeah. Yes.
So have you thought about how you could use geophysical survey to actually monitor the EOR process?
That's a really good point. The way that we were taking a look at this mostly, we're just kind of trying to find a place where those injector wells that would pump the fluid through the reservoir to really push the oil to the where you take the oil out the wells would be the most beneficial. So if you're putting it
the geometry.
Yeah, so if you're putting it right at the edge of the reservoir, you would be able to push much more of that leftover oil within it than if you were to put it somewhere more in the middle where you've already drained a lot of that kind of oil and gas.
Speed reading 101.
All right, so we are team 2, and our app idea is to do with dams and identifying piping within dams. So obviously everyone knows dams are widely used for water retention, electricity generation, and mine waste storage. A lot of these are earth-fill dams, basically constructed of whatever pore material they can find on the site. And a common failure method for earth-fill dams is piping. So piping occurs when soil particles are dislodged by water and migrate towards the downstream face. This can lead to erosion of the dam toe and potentially catastrophic failure. So our idea was to be able to use geophysics to identify piping before this failure and help identify possible mitigation measures.
So our host material is drier, compact soils, while the target material is going to be water or more dense patches of saturated soils. Therefore, we can use a DC resistivity survey to exploit the resistivity contrasts between the drier soils and the piped water. Since it's relatively cheap, we can also use multiple surveys and repeat it in different time intervals, even when piping is not suspected.
Okay, so in terms of choosing the array, we know the depth of the investigation. In this case, it's just going to be the depth of the dam. We also want it to be quite simple as we want to conduct the survey over and over again. So for this one, we chose the wonder array. Basically, the depth of the investigation can be determined by a set length of the array, and then a baseline can also be made for when the piping is not occurring, and there's no piping under the dam. And for the data, it's basically gathered along a profiling line that runs parallel and over top of the dam. This data can be transformed into a pseudo-section of the dam, and this just allows us to see that if any piping is occurring in the dam, it'll show up on the pseudo-section made by the survey.
Yeah, so the pseudo section is really the most important part of processing the data. It's all we need because what we're doing with it is we're comparing it to the parametric DC survey app. So we will change the different parameters of the app to try and model what we see in the real world with the app. There are a couple of changes that need to be made to the app. We want to be able to tailor like an actual dam's morphology to the app, so changing layers and stuff. We also have to change what we're targeting. Instead of a pipe, we're looking for water or, as we said, saturated soil.
All right, in terms of synthesis, what you want to do is check if the water is actually there. So you could use like a piezometer or another such technique, and then you would take actions to mitigate the piping, try and stop it before catastrophic failure occurs. So just in conclusion, we're trying to address the problem of piping in earth-filled dams. We're going to use a DC resistivity parametric inversion app to analyze a pseudo-section to actually locate and mitigate the piping that's there. Thank you.
So you want to see the piping, right? So have you thought about the physical property contrast between kind of the dam itself and the piping or whatever you're looking for?
So depending if it's water or if it's more of a densely saturated soil, the contrast will be a little bit stronger if it's just water and not as strong if it's just densely saturated soils. It also depends on the type of earth material that they're using, if it's more clays versus if it's more gravels and sands. If it's water versus gravels and sands, the contrast is going to be more higher orders of magnitude of a difference versus if it's just saturated clays, it's going to be less of a contrast.
Yeah. So what could be kind of important to see it's like you want to see this, you want to evaluate the interior of the dam, right? So and you want to use a DC. So what can be the situation where DC can play a big role? I wasn't exactly sure because it seems like pretty complicated, that contrast between.
It'll depend more on the earth materials that the dam is made out
of. So do you consider using this then in a monitoring format, or
more like a monitor, I think, because you would get a baseline survey. You create like a baseline pseudo section, and then if you see like you could do this seasonally or something, different water levels varying. And then like if you see any variation between the pseudo section that you're using as a baseline and the pseudo section you just gathered, that's when you would actually use the app maybe to try and locate the piping, and then take like it's there because the pseudo section is different.
So if you thought about doing this in different seasons.
Yeah, so you probably have to make a different baseline seasonally. Yeah.
Final question. Why did you choose winter?
Because it's a simple array and you can use it in profiling, but I guess the survey type wouldn't really make much difference.
Good, thank you. Okay, thanks guys. Those are great talks, interesting examples. So we'll see you tomorrow.